All right, so this is the CIS256. Today we're going to talk about um, binary heap, which is a special topic in the tree chapter with trees and stuff. So we'll see how the binary heap related to the tree structure and so on. All right, so what are binary heap? Okay, so in the earlier chapter, we talked about a queue or a first in, first out data structure. So when people are lying in the queue, the one is in the head of the queue will be served first. So first in, first out. Now, sometimes we not only need a queue, but also want to assign a priority to the members in the queue. For example, if you have a nightclub, a popular nightclubs, and the doorman of clubs, they want to arrange person by the amount of money they pay to the doorman, right? The more money you pay, you get a higher priority, so you get placed in the beginning. So that's a kind of priority queue, and in this particular queue, what's the data structure you're going to use? Okay. So in this picture, you can see the front of queue has the highest priority, back of queue has the lowest priority. So at any time, that's the property you're going to maintain, right? So if you are if you pay more money, you're placed higher priorities. That's that your position is higher. But if you want to insert a new item or new people coming, right? You depends on how much he or she pays, he will be inserted to the queue by the order of the money he pays. So that sounds like a pretty complicated. I mean, like not complicated, but you can implement this right using a sorting algorithm. So every time you have a new person coming into the queue, but you have to sort. So the best sorting algorithm we learned so far that involves comparing two numbers or items is about the order of n log n complexity, time complexity, right? So every time you have a person, if you have n person, you were going to do n log n operation to have this sorted. But we can do better, right? We can do it in a better, how about can we do it in ON, another way, right? So that's where the binary heap come into play. So in binary heap, we can quickly insert the person according to his priority in O log n, and we'll see how we do that, right? So just some heads up, when you diagram the binary, usually we draw it like a tree structure with root nodes. Depends on the type of binary tree, that binary heap. So like I said, you can have the maximum number on the top that we call the maximum heap, or the minimum number on top of the tree or root of the tree. It's called a minimum heap. Okay. So it's more like it's look very like a complete tree. But when you implement it, we're going to implement in a single list or array. So that's a trick for the binary heap. When you draw the picture in your head, you'll imagine a tree-like structure, but when we implement it, we use a array. So we'll see how it goes, right? So here is the abstract data type for a binary heap. So we have a constructor, which creates a minimum min heap. We're going to use the minimum heap as the example. And you can insert item, and we can find the minimum, which is the top, which is like O1. It's very quick because it's always on the root of the tree or the first item in the list. And then delete minimum, you just remove and return the minimum value. And it's empty, and you can build from the list. Python has a built-in collection model library to heap. You can heapify a list. So the way you do a binary private queue in Python is you using a heap library. Okay, so but we're going to talk to you how to build a binary heap from your own. So although Python have its own, we're gonna build ourselves so you understand. So here is the picture of a complete, almost complete binary tree. What I mean by complete is, first of all, you can see it's balanced, right? You fill each level is leveled left and right children before you fill the next level. So if this is empty, you don't fill the next level, you fill this, right? Until this level is full, then you start to build the next level. So only the last level can be imbalanced, but for the rest of them should be full, right? So that is called a balanced tree. Okay. So again, like I said, the only thing that you can be missing is on the leaf node. And it only goes from the left to the right, so it has to be the right side of any nodes known on that level. Okay, so here is the level number and number of nodes. Let's look at this property. The first level 0, which has the root nodes, it has a 1 node, right? So 2 to the power of 0. And on level 1, you have 2 nodes, left and right. So it's 2 nodes, 2 to the power of 1. And on next level, because each node has 2 nodes, so it's 2 times 2, so it's 2 to the power of 2, and so on and so forth. So for level n, it's 2 to the power of n. Think about it, right? This is a very important property you're going to use later in the heap, binary heap. Binary heap is binary built upon the binary tree idea. So every time you go to the next level, it's going to be 2 times more than previous level. Okay, so if you have that in mind, we can actually compress or convert this tree into a list. So this list, because of some arithmetic properties, I'm going to keep the zeros index with empty nodes. So the root starts with index 1, okay? Well, I'll let you know why we're doing that, okay? So level 0 is corresponding to this cell. And level 1 has left and right children, has 9 and 11, which is index 2 and 3. Now, and then next level, it has 4 children, 4, 5, 6, 7. Next level have 8 children, 8, 9, 10, and 2, 15. Okay, now you see this property. So there's a one-to-one mapping, right? So you won't, because the complete binary tree is nicely can be compacted into this nice list and with 0 index empty. Okay, so why we're doing that? So you can discover that for any node P, the left child is in that list. So what's the index of left child in that node? Well, given this index I for the P, which is number 1, right? Index 1, and the child of that is in 2p plus 2p or 2p plus 1. So 2p is 2, 2 plus 1 is 3. So 2 and 3 belongs to the child of 1. Now let's look at the child of 2. That's in level 2, right? So the child is 2 times 2 is 4, and 2 times 2 plus 1 is 5. So 4 and 5 belong to child of 2, and 2 times 3 is 6, and 2 times 3 plus 1 is 7. 6, 7 belong to the child of 3. So as you can see, for any node P, if you times 2, you get the left node. If you times 2p plus 1, you get the right node. And conversely, if you have a node, you want to know the parents, what do? You can just divide by 2. So 4 divided by 2 is 2. 5 divided by 2, if you do integer division, is still 2. So if you do integer division, then you will get the same parents. So now this is a very important concept in a binary tree or binary heap. When you want to do, for any node index, if you want to know the parents, you just divide by 2. Division. If you want to know its left children, you times 2. If you want to know the right children, it's 2p plus 1. Okay? Unless this is the leaf node and there is no right children, then it's just 2p. Okay, so this concept is very important because we're going to use that property to insert and delete nodes and still maintain the binary heap property. Okay, So here is the constructor of binary heap class, where simply internally the heap list is the list with the zeros index already populated with 0. The size is 0 because we're not going to use it, so it's pre-populated. Okay. Now let's insert some new items. So we can just append them to the heap. Okay. And then we can talk about how to keep the priority or range, right? So what's the priority? What's the property of the heap order? Right? So the heap has a special property. That means in a heap, so like I said, priority is like priority key. For every node X and its parent is P. How to get a parent? X divided by 2, right? That's the index of parent with parent P. The key value as a key in a P parent is always smaller than or equal to the key in X. That's a minimum heap property. So if you look at this, is this, so for example, if you look at this binary heap, is this a minimum binary heap? You can, you want to check, okay, so first level, first level, 5, his key, 5 is smaller than both his children. So that's okay. For 9, he's less than both children. That's okay. For 14, he's less than 33 and 17. It's okay. 18 is less than 27. He has no children. So that's okay too. 11 is less than 19 and 21. So this is a good binary heap. Okay. What if we want to insert into the binary heap? Well, you typically insert to the end of the list, which corresponding to the leaf node, the last leaf node of the entire tree. So that's 7. Now the 7 may not be satisfying the property of it's going to be the heaviest, right? 7 is lighter than 18. So what do? Well, you swap them. You swap them so that 7 is now less than both children. Are you done yet? This action swap, okay, swap, and then you compare 7 to 9 parents. Oh, it's still smaller, so you're going to swap it again. And you compare 7 to 5. That's okay because it's bigger than 5, so it stay as is. This process we call the percolating item up, or sometimes we call it swim up. Right? So you insert to the bottom of the tree, which is corresponding to the last element in the list, and then you just percolate up. While you just compare with the parent. How to get the parent index? Remember, his index divided by 2, interdivision. So you can compare them and you swap them if it's less. Otherwise, you already in a right position and you return. Here's the code. So we call the function perk up or swim up with index I, right? I is the index for that number to be perk up considered. So first of all, we check a while loop when it's integer division by 2, basically means his parent is greater than 0. Because if 0 is not used, right? If you get 1, that's the root, but 0, it means there's no parents with index 0. So that even just means you have a parent. Now, if you have a parent, and here, if the i's number in that heap list, remember it's a list, although we think about it as a tree, okay, but eventually it's list, is less than its parent, divided by 2 is parent. That means, because this is a min heap, so you're supposed to be greater or equal to, right? If it's less than, it's out of order, we fix that. The way you fix it is you swap that parents with you, all right? And you percolate up that you put index to divide by 2. So you go to the parents and repeat, rinse and repeat until you don't have a parent anymore. So that's fine. So that's percolate up. Again, the key is you understand the I integer division by 2 is a parent. And that's it. You keep finding the parent. I remember I's left children is 2 times I, his right children is 2 times I plus 1, and his parents divided by 2. If you remember this, then everything else should be easy. This is just swap, right? All right. So if you want to insert, you can use this percolate up. First of all, you append at the end of number k, and you add 1 to the size because you add one more element, and then you call the Perkle up with the current with the last index, and then you're done. Okay, so that's Perkle up. So now you ask, how do I removing the smallest element? This is easy because it's always at the top root node, right? Because the property of this binary heap is always at the top or the first element in a list. Once you remove it, then we have empty hole in our complete binary tree. So it's not complete anymore. What do you do? Well, we can fill it with another number in the tree. But you have to make sure after you fill it with a number in the tree, you have to maintain the heap all the property. Okay. So typically what you do is when you pop up the root, which is lightest one or the smallest number, you want to take the end of the number at the end of the list. Usually it's the biggest one. Yes, yeah, it should be biggest one. Well, bigger than the children, right? May not be bigger than its neighbor, so that's fine. So yeah, but you take the last element and put it into this top position. Now, 27 obviously is heavier than both of children. That's fine because we're gonna do is swap them, the left with the left children, or actually swap with the minimum children, because 9 and 7, 11. If you want to make it lighter, okay, you want to swap with a light, minimum children. So this one is also lighter than 11, right? So you swap with 9, not 11. So now here you compare with 14, it's still heavier. You swap with 14, right? Because 14 is smaller than 18. And then here you swap with choose is bigger than 17, swap with 17. 17 is the smallest children. And then you're on the leaf, you're fine, it's done. So 9 became the new lightest root. That's percolation done. Translating to code, it's very simple too. I learned and understand this formula. So the exit condition is the children, which is current node times 2, which is the children is less than current size. So it's inside the boundary of the current list. And you find the minimum child of that node I. Now, the way you find the minimum child here is the helper function is to compare both children. Remember, the left children is 2 times I. The right children is 2 times I plus 1, the index of the left children, okay? So if I times 2 plus 1, the right children is greater than the current size, that means there's no right children, then you just return the left children, which is I times 2. Otherwise, if you have both children and the left children is less than the right children, then you return the left children. Otherwise, you return the right children. Okay, so this is the whole algorithm for finding minimum child, and you replace with the index of the minimum child, or replace the number with the minimum child. If the number is greater than the minimum child, right? Because it's Perkle down, then you just raise them, and then you assign I equal to minimum child, and keep going until you find this position. So when you delete the minimum, you can simply return the heap list number index 1 because that's the root, and then you change that. You override the 1 with the last element in the list in the heap, and you decrease the size because you popped 1 already, and then you percolate down 1 because this 1 index and 1 is the new is not proper yet. You haven't checked it, so you just percolate down to check it. Okay, so because at that point it's the last element. Okay, so that's the whole thing you need to remember: percolate down, percolate up. And that's all there is to it for the binary heap main operation to maintain the property of binary heap. Okay. So usually in Python, you keep a unordered list or just simply random number in the list. You want to make a minimum heap, you can heapify that list. Okay, that's called heapify, and it's O(n) of time. Now I'm gonna now mathematically prove that, so that's just in the book. All right. So the last note is, given that minimum heap property, there's another way to store the number of in a list, because what you can do is you keep delete. First of all, you heapify it, which take O(n), and then you delete the minimum, because the first element in the list is always a minimum. Just keep deleting and perco up, right? Perco down to maintain, and you keep deleting. So every time you perco down is log n, and you have n numbers. So overall, you have O(n) log n time to maintain to sort. Basically, you're sorting a new list, right? So that's called heap sort, by the way. It's also n log n. All right, that's all for the binary heap. See you next time. Bye.